Earth Science, the crystallization of minerals and silica enrichment. Earth's crust is made up of rocks, and these rocks are made up of minerals, and the minerals are made up of elements. Looking at the composition of Earth's crust, we see that half of the crust's mass is oxygen, and about a fourth is silicon. When these two elements are combined, the compound is called silica. Knowing the percentages of elements in Earth's crust, it makes sense that most rocks will have silica as part of their chemical composition. And that brings us to mineral classification. Minerals are classified by chemical composition, and the two main categories of minerals are those that contain silica, the silicate minerals, and those that do not, the non-silicate minerals. Silicates are the most common mineral group. They make up more than 90% of Earth's crust. The non-silicate minerals make up about 8% of Earth's crust. Non-silicate minerals include the carbonates, oxides, phosphates, sulfates, sulfides, halides, and the native elements. These mineral groups are all important, but for now we're interested only in the silicate mineral group and how silicate minerals form and crystallize from magma. Minerals are formed by crystallization. Crystallization starts when atoms begin to bond with one another to form a particular geometric pattern. As the number of atoms and bonds increase, a single crystal forms. And as more and more atoms bond to the microscopic crystal, the crystal grows. Minerals commonly crystallize from two different sources, from magma, molten rock, and from water solutions. Igneous rocks are formed from magma, and certain sedimentary rocks are formed from water solutions. Let's look at the crystallization of magma. Magma is composed primarily of the elements found in the silicate group of minerals. And all silicate minerals have the same fundamental structure of atoms, 4 oxygen atoms surrounding a single silicon atom. When magma starts to cool, the atoms lose kinetic energy, and attractive forces pull the atoms into their orderly crystalline structures. Minerals crystallize from cooling magma in a systematic fashion, based upon their respective melting points. Melting point may sound a bit confusing since we're talking about crystallization, so let's think about the analogy of ice and water. Ice melts at the same temperature at which water freezes. And it's the same thing for minerals. A mineral's melting point is the same temperature at which it begins to crystallize from hot magma. The crystallization point, and hence melting point, of silicate minerals depends on the amount of silica they contain. Magma is very hot. As magma cools, the first minerals to crystallize have a high melting point. They are able to crystallize at very hot temperatures. These high melting point minerals also have the lowest amount of silica, so high melting point, low silica content. Then the last minerals to crystallize have the lowest melting points. They melt when the magma is much cooler, but they have the highest silica content. Low melting point, high silica content. The crystallization point, and hence melting point, of silicate minerals depends on the amount of silica they contain. Magma is very hot. As magma cools, the first minerals to crystallize have a high melting point. They are able to crystallize at very hot temperatures. These high melting point minerals also have the lowest amount of silica, so high melting point, low silica content. Then the last minerals to crystallize have the lowest melting points. They melt when the magma is much cooler, but they have the highest silica content. Low melting point, high silica content. This diagram shows the step-by-step crystallization of silicate minerals. Olivine has a very high melting crystallization temperature and is one of the first minerals to crystallize from a magma. After olivine forms, the mineral pyroxene can form, followed by the amphibole minerals and the mineral biotite. These ferromagnesian silicates form in a step-by-step process. Calcium-rich plagioclase minerals also form at high temperatures, and as temperatures cool, the sodium-rich feldspars form. And as temperature continues to cool, potassium feldspars form, followed by muscovite, and then finally quartz minerals. With each step in crystallization, the silica content of the remaining magma increases. It is silica enriched. So later formed minerals have a higher silica content than early formed minerals. Onward!